Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your Zybooks section 10.7. It's called Counting by Complement. I'm hoping that word complement sounds familiar. When we talked about sets, I think back in chapter 3, you saw what the complement of a set was, right? It was everything in the universal set that wasn't in the set. So let's get into this. Alright, so suppose we want to count the number of people in a room with red hair. And we know that there are 20 people in the room, and exactly 12 of them do not have red hair. Then we can deduce that the number of people in the room with red hair is 20, right, the set of all people, minus those that don't have red hair. And then you get the number that do. Right, 20 minus 12, there'd be 8 people in the room with red hair. This is called counting by complement. You take the number of elements in the entire, in the universal set, take away all the elements that aren't in the set that you want, and you'll get the number of elements in the set that you want. All right, this is counting by complement. Is a technique for counting the number of elements in a set S that have a property by counting the total number of elements in S and subtracting the number of elements in S that do not have that property. And the principle of counting by complement can be written using set notation, where P is the subset of elements in S that have the property. So if I want to know how many people have property P, I count how many people are there total, how many elements are there total, and then take away all the elements in the complement of P. They say a P bar. Take away all the elements that don't have that property. All right. And give you an example down here. I'll actually write this one out on paper. All right, so the question is, how many bit strings of length 8, or how many 8-bit strings have at least 1 0? How many 8-bit strings have at least 1 0? Now, let's say S, if I'm using the same letters that they were using earlier. Let's say S is the set of all 8-bit strings. All right, now the cardinality of S, all right, is 2 to the 8th. Right? Because there's 8 bits and each one of them can be either 0 or 1. So the total number of 8-bit strings, the universal set, has a size of 2 to the 8th. There are 2 to the 8th elements. Now let's say P is the set of elements with the property we want. Right? This is the set of all 8-bit strings with at least 1 0. With at least 1 0 in it. Right, and we want this cardinality, right? We want the cardinality of P. This is what we're asked to find, right? How many of these are there? So the cardinality of this set is, unknown at the moment. So in order to do this in a quick way, because you could do this a long way, when I say at least 1 0 in it, that means having, exactly 1 0, or exactly 2 zeros, or exactly 3, or exactly 4, or exactly 5, or exactly 6, or exactly 7, or exactly 8 zeros. And I could find how many have exactly 2, exactly 1, exactly 2, exactly 3, all the way up to exactly 8, and then add all those up. But that would take too long. Instead, let's look at the complement of this set P, right? Let's look at the set of all the elements of S, right? All the 8-bit strings that don't have this property. So the complement of P would be the set of all 8-bit strings. Now, what's the opposite of having at least one 0? The opposite of having at least one 0 is having no zeros. So the set of all 8-bit strings with no zeros. Now this is a lot easier to calculate. The number of 8-bit strings with no zeros. Well, there's only one of those. That would be the 8-bit string 11111111. That's the only 8-bit string with no zeros. So the cardinality of P bar, right, the complement of P, is 1. And then by that complement rule that was shown to us in the text there, the size of P, right, the number of 8-bit strings with at least one 0, is the size of the entire set of 8-bit strings minus the size of the number of strings with no zeros. So this would be 2 to the 8th minus 1. And let's see, 2 to the 8th, 32, 64, 128, 256 minus 1 is 255. So there are 255 8-bit strings that have at least one 0. And there's only one that doesn't. But you see how much easier that was to count? Because instead of counting how many have 1 0, how many have 2 zeros, how many have 3 zeros, how many have 4 zeros, how many have 5 zeros, all the way up to 8, and then adding those up, instead of doing all that, I just look at the opposite. How many have no zeros? And then take it away from all 8-bit strings. And it's a lot quicker. And again, they kind of run you through that here. 255, great. Okay. So let's take a look at some examples here. So here we're asked to give numerical answers for the questions below. All right, there are 10 kids on the math team. 2 kids will be selected from the team to compete in the state competition. How many ways are there to select the 2 competitors? Well, this one doesn't involve really any complements. This is just a combination problem, right? So there are 10 people on the math team. I said 10 kids on the math team. And you're selecting 2 of them to go to some competition. And it really doesn't matter what order, right? So you see order doesn't matter here. So this is a combination or a subset problem. Because I could have, Alice and Bob or Bob and Alice. Doesn't matter. They're the same 2 people. Order doesn't matter. So this is simply 10 choose 2. Remember this notation? Or that C with the 10 comma 2. Or that 10C2. All these are the same thing. And this would be, the number of permutations. So 10 times 9. But then divided by 2 factorial, which is just 2. So this is 45. 90 divided by 2. So this one didn't involve complements, but we'll eventually get there. I see one of the problems later in this activity does involve, or it'll be nice to involve a complement. So 45. Right, so there are 45 ways to pick 2 kids out of this team to go to this competition. I don't know why I just typed 2. 45. Okay, 10 choose 2. All right, number 2. Okay, change it up a bit. The math team has 6 girls and 4 boys. How many ways are there to select these 2 competitors if they are both girls? Right, if they're both girls. So now, again, same 10 kids, but now they broke it up a little bit more. They said 6 of them are boys, 4 of them are girls, and now they're saying select 2 girls instead of just select 2 of any of them. So I'm not picking from all 10 of them now. I'm picking from just the 4 girls. So again, that would just be a combination of these 4 girls. I'm just going to choose 2 of them to go to the competition, right? Alice and Sally, Sally and Alice, right? It doesn't matter what order they come in, so it's still a combination problem. And this would be, 4 times 3, the number of permutations divided by 2 factorial. That's 6. So there'd be 6 ways of choosing exactly, 2 girls to go if the team was broken up this way, 6 boys and 4 girls. Okay, so this is 6. Oh, it said 6 girls and 4 boys. My apologies. Oh boy. Oh boy. Other way around. It said 6 girls and 4 boys. Oops. So scratch this. Alright, scratch that. My apologies. So again, selecting 2 girls. So I'm selecting from the 6 girls, right? So it would be 6 choose 2. And this would be 6 times 5, the number of permutations divided by 2 factorial, which is 2. This is 15. Right? So there'd be 15 ways of selecting 2 girls if the team was broken up into 6 girls and 2 boys and you were selecting 2 girls. So this is 15. Alright, now the same team, right? The math team has 6 girls, 4 boys. How many ways are there to select the 2 competitors so that at least 1 boy is chosen? Right, so this one would be nice. I'm going to tell you, involving a complement will be nice here. Back to the paper. So again, we have 6 girls, 4 boys. And now we're selecting 2 competitors. Select 2, and you must have at least 1 boy. Now, you could do it the long way. I could say, how many ways can I choose them so that one of them is a boy, and the other one's a girl. But I'm going to do that complement way instead, and then I could also look at the way how many ways can I select them so that both of them are boys, right? But I'm going to look at that complement way. So let's say P is the number of ways to select 2 such that at least 1 is a boy. And then look at the complement. Right. Now the opposite of that, at least 1 boy means no boys. Right? At least 1 boy means one or more. The opposite means no boys. Right. So this is the number of ways. This would be the number of ways to select 2 with no boys. Well, if there's no boys, that means both girls, because again there's only boys and girls in this problem, and we saw that already. This was 15. Right, this was 15 that was the previous question. That there's two girls on this team is meaning I select no boys. So that was this number here, right? 15. And then the total number was 45, right? So let's say S was the number of ways I could select 2, and then the cardinality of S, right? The total number of all the ways I could select 2 of these kids was 45. So then using that complement rule, the number of ways I can select 2 kids and have at least one of them be a boy would be the total number of ways to select 2 kids minus the number of ways to select 2 kids with no boys. And this would be, the other 30. Right. So this should be 30. Right. So they eventually led up to using a complement. Right. Here, 4 people, John, Paul, George, and Ringo, are seated in a row on a bench. The number of ways to order the 4 people so that John is next to Paul is 12. And you actually saw this in the permutations section. I believe that was section 10.4. So the number of ways you can put these 4 people in on a bench, where order matters here, where John is next to Paul, there's 12 ways to do that. How many ways are there to order the 4 people on the bench so that John is not next to Paul? Well, think about it. Remember, there are 4 factorial, there's 4 people. There are 4 factorial ways of putting them on this bench, reordering them on this bench. So that's 24. 4 factorial is 24. And there are 12 ways of putting John next to Paul. Now I want John not next to Paul, so we subtract those. Take 24 minus 12. We're going to use the complement rule to get the number. So that's still 12. And then go through the complement there. All right. So then your challenge activity, you're counting. You're counting again. Now, if you have any combinations, you're going to enter them with the C notation. I'm sure any permutations that come up will be entered with the P notation. So here, an auto dealer has 7 different cars and 5 different trucks. How many ways are there to select 2 vehicles? Well, 2 of any kind of vehicle, right? So it doesn't matter if it's a car or a truck or what order you're selecting them in. So there are 12 vehicles and you're choosing 2 of them. So this is simply 12 C2, right? 12 choose 2. Or 66. Here, a shop has 8 different shirts and 6 different jeans. How many ways are there to select 2 shirts? Well, you're not doing all 14, right? Because it's shirts and jeans. You're only selecting shirts. And it doesn't matter what order, right? You're just choosing 2 different shirts here. So 8, choose 2. All right. 8, choose 2. And 28, simple. All right, now look at this. At least 1 jeans, or a pair of jeans, is chosen. Here I'm going to, I see that at least 1. I'll probably use the complement rule here. A shop has 7 different shirts and 6 different, pairs of jeans, types of jeans. How many ways are there to select 2 items so that at least 1 pair of jeans is chosen? So I'll pull up a piece of paper here. So the total number of ways to select objects here, there are 13 items of clothing. Right? There's 7 types of shirts, 6 types of jeans, so 13 types of clothing. And the number of ways to select 2 of any of them, right, would be 13 choose 2. Now that would be 13 times 12 divided by 2 factorial. That would be 13 times 6, 78. All right. So there'd be 78 different ways of selecting, two different things. 2 shirts, 2 jeans, a shirt and a jean, whatever. Now, they want at least 1 jeans, right? The number of ways of grabbing 2 items so that at least 1 is jeans. Well, remember the complement of that. The complement of this, the opposite of at least one of them is jeans, is no jeans. And no jeans means all shirts. And the number of ways that can happen, there are 7 different types of shirts, and choose 2 of those. All right, and 7 choose 2 would be, 7 times 6 divided by 2 factorial. That would be 21. And so the at least 1 jeans, how many ways can I select 2 objects, 2 items of clothing so that at least one of them is jeans, is I take the total number of ways of selecting 2 objects and then take away the number of ways of selecting no jeans. All right, and 78 minus 21 is 57. There'll be 57 different ways. Now I think you could type in either 57 or I could type in 13 choose 2 minus 7 choose 2. All right. I'll just type in 57. See if I get it. Yeah. See, 13 choose 2 minus 7 choose 2 using that complement rule. And I guess I'll leave the last one for you. And you might see different numbers that I'm seeing here, but I'll just leave the last one for you. All right, so hopefully, again, this complement rule makes sense. If you want the number of objects, the number of ways to, or you want the number of elements that have a certain property, you take all the elements, right, all the elements in the universal set, and then take away all the elements that don't have that property, right, the complement. And then you have your additional exercises, which I think all of these are assigned. There's only 4 of them with so many parts. But if they're not, I would still recommend looking at all of them. Trying them all out just to get more practice, more exposure to the material, maybe get better at it. And you got the solutions to look at too if you want. But please try to work on the problem. Try to figure things out before you look at the solutions. Don't just copy solutions down, because you're not going to learn anything that way. And of course, if you have any questions, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.